this is going to be a technical talk, two technical talks. I'm sorry, it will be technical in nature, but it will have no formulas, so it's going to be at the same time technical and without formulas. But the idea is that what I'm going to transmit to you here is a technical fact. Unfortunately, this is, it's going to be a bit, let's say, it concerns the things we know and the way we calculate them. So, okay, that's for disclaimers. So, to start, people ask, there's always the question of the glass problem, and so often people ask, but what is the problem? Why is there a problem? So let me tell you one way of saying that there is a problem. So what we know about liquids is that when we supercool them, if they don't crystallize, what we see is that something, which is a time scale, typically the viscosity or related to the viscosity, blows up until at a certain point the system falls out of equilibrium, and then this curve, once you fall out of equilibrium, it doesn't keep on rising. In this case, what I am changing is either making the temperature lower or the pressure higher. I will use always pressure and 1 over pressure and temperature as playing the same role. So this explodes by 14 orders of magnitude. But of course, we do not know. The slower we go, the higher this curve goes. If we go very fast, it will level off. But if we go very slowly, it goes further up. And the question is there a divergence in this time? So if there is a divergence in viscosity, it means that we have obtained a solid, a real solid, which has zero viscosity. So the typical time scale, which it takes for reorganizing spontaneously, is infinite. So we don't know, and I don't know if we will know, but for the moment, we don't know if such a divergence exists. What we see is that there are many orders of magnitude in which this explodes. Now, where is the problem? The problem is that one thing we know, and it's quite amazing that it's not clear to everybody, is that in order to have a divergence in time scale at finite temperature, you need that the different, oh, gray doesn't pass, okay. So here there was a picture. You need that different subsets of your system do not thermalize in parallel. So if this part of your system and this part of the system can arrange themselves to be in equilibrium without talking to one another, this, then you would expect that the equilibration time could be finite. If instead they don't, then you would say you have order. Just to give you an example, if you had a crystal, you would be preparing your crystal here, which locally would be producing the crystal lattice. Somewhere else, this would be happening at the same time. But these two guys have to talk to one another at some point to say to one another, listen, you're not in the right angle. We have to get our thing together. So this is a theorem by now, but this is everything you need to know for the moment, that if you want to have something that really has a divergent time scale, then you need that the system needs to exchange information at long distances. And if you need really infinite, then you need that this happens at every distance. In other words, you can only have a divergence in time scale, or equivalently, you can only have a true solid if there is some form of long-range order. Now, the problem is that when you look at a photo of a glass, of the atoms of a glass, it doesn't look very different from a liquid, so, which is very disordered. So the problem is, and now this justifies the word problem as applied to glass, how can it possibly be that you have a length scale that seems to diverge, and yet no order that you can really see. Now, there are two ways out of this dilemma. One is to say, yes, there is an order, but we are not smart enough to actually be able to compute it. For translation, it's clear that Fourier transforms will do, but for this, Fourier transforms are too primitive, too dumb. But the other thing is to say, no, there isn't a divergence. This will eventually level off. And eventually, of course, you might have a divergence at 0 temperature. Of course, at 0 temperature, you need no order to have a divergence. Just a double well will do the job, because you just don't cross it. So this is one word why the glass physics is described as being a problem. The problem is you need order, but you don't seem to have it. But maybe you don't need it, and maybe the length of coordination, if you want, that you need to get this time scale is very short. It is indeed very short, 3, 4, I don't know, atom distance. And that's all there is. And the length scale grows, but stops at 4, 5, and that's the end of it. For your physics, it's good enough. For your matter of principle thing, you would like to know whether it's infinity or not. Okay? So this is a bit out of line with what I'm going to continue to do, but I think that it's a nice thing to say. Okay, so random first order scenario. My talk is going to mainly be about this, about mean field models of glasses. So random first order scenario was born again. Gray is not visible. It's going to be problematic. There was the name of Kirkpatrick, Tirumala, and Volines in gray here. So they made the following guess. They said, this is a model for a spin glass. If we make these Jij's random so that these spins interact through random plus and minus interactions, and for example, you make it fully connected, the spins are plus minus 1, this is the mean field model for spin glasses. It's called Sherrington-Kirkpatrick if it's fully connected. It's called Edwards-Anderson if it's on a lattice. And everybody knows, everybody accepts, or most people accept that this is a good model for spin glasses. Now, they made the following guess. They said, well, if I did the same thing, but with p-spin interactions, so more than 2 spin interactions, then the spins can be plus minus 1, or they could even be spherical. Spherical constraint on the sphere is technically easier. There is no way of justifying it, but it's technically very easy to treat. Anyway, this doesn't change anything, but they guessed that if you had more than 2 spin interactions, then this was the mean field model for glasses. Not for spin glasses, but for structural glasses. So I'm going to work on this, but let me tell you how they got to this guess. So when you do this spin glass, the mean field spin glass, you have the paramagnetic phase, where essentially everything moves fast. Then you have a power law divergence of times. You have a transition, a single transition, and then below this transition, you have the glassy phase, which is composed of many states. Many states, you will see many valleys, is a common element of all theories. But there is a single transition, and from here downwards, the system is in a critical state. Maybe here some gray is visible. Here there is a well that is a bit rounded. Here there is a well that is flattish exactly at the critical temperature, like in a ferromagnet. But below, you have a situation where you have a landscape that looks like this, with very small barriers, not even order of the size of the system, and many states. And this is all the way down. It's critical because each one of these valleys is flat, as if it were itself undergoing a transition of this kind. So each of the many states you have in this thing looks like the one that is flat here. So look at one of these, and itself, it looks like this at its inside. It's not around it. This means that some susceptibility is going to diverge, because if you push in that direction, it's going to be particularly easy. So there you're going to get a... This is what happens, and it was well known at the time that these guys made this guess. Now, when you do p larger than 2, doesn't matter which of these two, you get something that is very different, and it will take us a lot of work to describe it fully. So what happened is the following. You have a liquid phase. Liquid and paramagnet in this language is the same. I call it liquid, but it's just a phase where everything moves fast and it has nothing remarkable. Here there is a divergence of your time scale, and you have a dynamic transition. So when your temperature crosses this point, we will come back to this many times, your dynamics becomes non-trivial. However, and this is what these people remarked, if you make a static transition of the equilibrium quantities, that nothing absolutely happens here. Everything is continuous up to a point that is well below, and this defines from this point a static transition. So they saw this fact. I don't know how they realized, honestly, that this was going to be the case, because the calculations you have to do, you really have to probably have guessed the result. If not, you wouldn't take the work of doing them. But the fact that you have these dual two transitions is the secret of why the physics is very different. Because now you have a liquid, you will have something that thermodynamically is a liquid, but in fact, dynamically it is very slow. We will come back to this. Then you have a transition, and then you have a thermodynamic glass phase, where the states are in principle not like this, but they are uncritical. So for me, this is critical, and this very round is uncritical, meaning that nothing diverges there. So they guessed that this double transition was going to be the model for what happens within mean field of glasses. Now, the moment they made this, of course, you realize that here there's not much from first principles. This is a wild guess on a kind of spin glass-like thing. So let me tell you so that you appreciate to what extent this was, once we understood it, quite an impact. So in a single stroke with this, they found that this model had a scenario for the equilibrium transition that had been the one, and we will come back to this, that had been discussed by Kauzmann, although he himself didn't take it very seriously, but that had been the scenario that had been proposed in the first half of the 20th century. Coming from a completely microscopic model. The same model had as a transition, so this one is the Kauzmann temperature. The same model, without you asking it, had here a transition that had been studied, that was fashionable, and it's called the mode coupling transition. We will also come back to this. So these two things that come from very different worlds, very different people work on these things, they happened together and without you doing anything in this same model. All these things are for structural glasses. Then there is a whole discussion that had been already done on how are the states structured, how many stable directions, how many unstable directions they have, et cetera, the deep ones, the shallow ones. This had been done a bit guessed by Goldstein. Well, you find it and it comes out naturally and you don't have to put it by hand. The whole scenario is comprised in the same model. Of course, you have the model, you have the Hamiltonian, so you can solve the dynamics. So you solve the dynamics, and what you find is, below the glass transition, the system doesn't equilibrate. This is the definition of glass transition. It evolves with, we will come to this also, all these things we will come back to, in a way that introduces a new temperature in the problem, which is inherent to the system. This was called effective temperatures, but then it turned out that the literature, even in the 40s, had the notion of fictive temperature. It was a phenomenological notion, so it was very elastic. Now it's a bit less elastic because you get it out of a calculation, but still, this came out naturally and without you putting it in, out of a solution of the problem. Similarly, you could do rheology. Rheology means move the system around with forces that don't derive from a potential, and you get the phenomenology of shear thinning, which was already well known for glasses. The system, if you let it go, it doesn't equilibrate ever, it ages, so it becomes more and more old without ever reaching a stationary state. What do I mean by old? More viscous. So if I quench a liquid to a very low temperature, it doesn't equilibrate, it becomes progressively more viscous with time. And then there was the justification that came in the problem and came out of a calculation still of an idea of Sam Edwards that nobody took seriously, I think. And for these models, his idea is precisely exact, which is that if you have many states and the system is aging, it will visit those states with equal probability. Don't ask me why this happens, nobody knows, but it gives you it is a remarkable fact that you find from these models. So in a strike, just by claiming that this model was a good model for glasses, a lot of ideas of the 20th century were captured and wrapped up into one thing. So I think Silvio was justified, this was 95 maybe, in organizing a congress that was called Unifying Concepts, and this was it. I mean, everybody was so impressed by all this combination of things that entered alone without you putting them by hand, that this seemed very, very remarkable. Now, not everybody believed, still, and the main criticism you can say, or you could say, is, yes, but where are the particles? You say that this is a model for glasses, but where are the particles? So, because you see, this spin model had no particles in it. Please, do stop me. Maybe the older people should stop me first, so this will create a precedent that will... okay, so now the situation has completely changed, because of the following reason. What used to be a very good, a remarkable intuition, now you don't need to have any intuition. We now know that if you solve the problem in large number of dimensions, it exactly does the same job that the p-spin does. So I could have started here and not do justice to the older work and say, listen, I am going to tell you what you get in dimension 1,000,000, and you will see that it's exact. And then you can do expansions in 1/d, and that's it. And this is what I'm going to do starting from now. So what used to be called random first order scenario, now you could simply call the mean field theory of glasses, because it's just high dimension, and it's a very common thing to do to put a problem in high dimensions. Very common thing to do means that people in strongly correlated electrons, in gauge theory, in atomic physics, where are all things where you don't have a small parameter, what can you do? So one thing you can do, for example, you want to solve for an atom that has 85 protons, what do? There's no parameter, so the one thing you can do is to put the quantum mechanics of 85 protons and so many electrons, and so 85 and so many neutrons, in variable dimension, solve it in the limit of infinite dimensions, and you get rather good results. You can do the same thing with strongly correlated electrons, and it has been a very productive way of thinking. And, well, this is applying the same to systems of particles. So why So large dimensions does the job that Kirkpatrick, Tirumala, and Bolines wanted for, or proposed for, and correctly for these p-spin models. I am mostly going to refer from now onwards to large dimensions because it implies no assumption. You don't need an intuition. Anybody who had solved all what we know today in large dimension without having any intuition would have obtained the same scenario. Okay, one word and only one, why a problem becomes easy in large number of dimensions. This is everything you need to know. All the rest is just working hard. If you have three particles and you want them to touch one another in threes, you have a number of configurations. Keep these two fixed and then look at how many ways you can put this one. And in 3 dimensions, you can turn it around, you see how, and there's a circle that tells you how many different positions of the third are such that the 3 are kissing one another. Now, do the same thing, not demanding that, and you see that if I put it here, you can move them on a larger circle, the one that is free. Okay, so there is more entropy to this configuration than to this one. I mean, to the demanding that 3 touch and to that they touch 2 by 2. Try it in more dimensions, and you will see that this ratio blows up to infinity. So the number of ways, and it's easy to see why, because the number of ways in which you can put the third one in 4 dimensions becomes a 2-dimensional manifold. In d dimensions, it becomes a d minus whatever, 2, d minus 1 manifold. And of course, when you have different radii in large dimension, you see that a small difference in this, it can make the ratio enormously different, no? A half to a million is very different from 2/3 to 1 million. So this is the technical reason why d dimensions is easy. The only thing you need to know is that all the encounters that you have in large dimensionality are tree-like. The others are very unlikely just for geometrical reasons. If you apply this ad nauseam, you get exact solutions in large number of dimensions. Okay? So this is the technical side. Okay, and it allows you to do everything. You can do everything with spherical particles interacting in large number of dimensions. And as I said, you recover the random first order scenario, which is no longer a scenario now. It is an approximation, large D, and which I'm going to describe very much in the next 45 minutes. An important fact, Patrick has done a lot of work on this and other people, is that now you can, these days, you can do simulations up to, I don't know, 12 dimensions and down to 3 or 2 dimensions. Now, for all practical purposes, it turns out that 12 dimensions is like infinite in the sense that whatever you computed at infinite qualitatively works perfectly. 3 dimensions has problems and limitations. You can turn the knob down from 12 to 3 and see how the limitations of your approach happen. Okay? So it's not a mad idea and that's all. You can follow it concretely in a simulation where you can see everything. So bear this in mind because it has been done with lots of things and it will probably be done with many others that haven't yet been clarified, but you can test this approach. Okay, so before I start with the random first order scenario, there are 2 general facts that I need to, that we are on the same page. So 2 impossibilities. Imagine that you had 2 states, like in a ferromagnet it could be up and down, spins. One is the red one, the other one is the blue. Imagine that the blue has a higher free energy density than, a lower free energy density than the red one. Question is, could both phases be stable? Or is the red phase stable? Or is a droplet of the blue, remember blue is better, is going to swallow, is going to inflate and kill the red? It's easy to do an estimate. You say how much you gain. So you gain the free energy density difference times the, sorry, D here is okay, but this is the radius of the droplet you're nucleating. How much do you pay? Well, you pay with a mismatch of the two phases, so it's a D minus 1. This is a kind of surface tension between the two phases. And when you do this calculation, you see that the worst moment is a certain size where you're paying a lot and you still don't have the benefit of the volume term. But this height, if this difference is finite, free energy difference, this height is always finite, meaning that you always have a finite droplet that will, after that point, continue to grow like mad. And if by chance you get to that size, the red phase is dead. The blue one will kill it. And so it's a matter of time that the red phase is going to die. So this is a very, very general argument. You cannot have metastable states that have a higher free energy density, order 1. Only if the difference goes in energy densities goes to 0 in the thermodynamic limit, you can have them. But otherwise, no. Okay. This is what is called the nucleation argument, and it's important for all the things we're going to say in the sequel. Another thing that is a bit less discussed is that even if they all had the same free energy, and you had many metastable states, the blue, but also a red, and also a green, and what have you, many different possible states. So it could be an object that has different forms of order. You cannot have an exponential number of them. This is much more subtle and perhaps a little bit less known. So you cannot have an exponential number of different states. In the same way that a ferromagnet has an up and a down state, you cannot have a system where the possibilities are exponentially many. Because as you grow, you have this blue thing that wants to grow, but the number of, because there are, if you assume that there are exponentially many, they have to coincide at least in some places, because you only can produce things out of the particles you have. And it turns out that all these combinations of possibilities, the more you grow, the more possibilities that are offered to you. And just because the number of possibilities is very large, this will make a droplet grow and kill your initial phase. It's a more subtle argument, but think of it in this way. This is an exercise that you can do for nothing. Take this cup in dimension n and do simply a Langevin dynamics here, so in contact with noise. Now you can go to radial coordinates. It's an exercise. And you will find that when you go to the radial coordinates, the barrier you have is your original barrier minus the number of dimensions times the temperature times the log of the radius. So this log of the radius is how many possibilities you have. You see, this is the volume of this ridge, for example. So you see, this is the multiplicity of possibilities of climbing and escaping is helping you to escape. There were lots of doubts about this. People used to say, but how is it possible that if I escape through one path, the fact that there are many others which I didn't take helps me to go out? Well, you can argue, but best of all is to do the calculation without much thinking, and you can get convinced that when you have an exponential number of doors, you are sucked up by at least one, as if there were a force that is pulling you out. If the number is exponential, this always dominates over a small energy, and you escape. So this is the reason here, when you have too many choices, in this model example, the many choices are the different directions, then what you have is never going to be stable. So the morals of this is two things that we're going to repeat a lot, is that, first of all, there cannot be a state with a higher free energy density, and secondly, you can never have an exponential number of stable states. They will have to decay into something else. Just because the number of possibilities of escape you have is exponential, you will take them. Okay? Bear this in...
I guess just
yeah.
I'm a little confused by this middle one. So the statement is you divide this up, tile this plane, and is this in
finite dimensions?
This is finite dimensions, so
Yes.
it's not an interdimensional one. And when you say exponential number of states, these are what are the states here? Spin up or spin down?
Well, you have to, yeah, well, precisely. I mean, imagine you had a quasi-crystal, no? Quasi-crystal never repeats itself. So if I have a big chunk, this is, and I want all states that live in this chunk, there's one, but then I move, and there's another one that is different, and then I move and choose another piece, and there's another. So you could have many of those. The answer, but the question is, you can never have, for a chunk this size, you cannot have an exponential number. That you can have many, it's true, the example of quasi-crystal tells you. You take a quasi-crystal that is 10 centimeters aside, now God gives you an infinite one, and you know that you could choose this 10 centimeter square from many places, and they don't coincide. So you are constructing many states for your chunk. Actually, the order is of the size of the chunk. It's not exponential. But the idea is, could it be for a glass that there are an exponential number of varieties, exponential in the size, in the 10 centimeters? The answer is no, this is not possible. In finite dimensions, you can never have an exponential. I'm telling you this because all these two arguments fail when you make large dimensions. And most of the theory on which we are sitting creates or is based on stable states of this kind and of this kind, which I am warning you from now, don't exist in finite dimensions. This is the warning that I'm... Now, it's an important part of the scenario that I'm going to discuss, that it invokes things that don't exist, okay, in reality. So much as I said that the scenario is fantastic and it sort of subsumes everything in itself, it is based on things that you always have to make a disclaimer afterwards. Yes, but careful, this doesn't quite exist. So you will see this happening now. This is what makes the whole thing subtle, because you are, on one hand, defending something, bearing in mind that it has clear limitations. And these two arguments are the basic limitations. Of course, a state that is metastable can exist, but then it will have a lifetime. And this lifetime could be 10 years, and so you're happy as an experimentalist, but as a matter of principle, you cannot say that it is a true state. Okay, so now to start. So what do we know? I will tell you later how do we know, but for the moment, let me tell you what do we know. This is going to be lots and lots and lots of time this same picture. So just in order to get accustomed a bit. So on this axis, I'm putting energy, or wait, if I put energy in this axis, I'm going to put temperature on this one. But I could be interested in hard spheres. And then the clever variable to use is 1 over the pressure. And the associated variable is the volume fraction, the maximal you can have, minus the one you have. Why did I write it like this? In order that as you go down, you have a denser system. So you compress and you have a denser system going down, or you lower the temperature and you have an energy that is getting lower. Okay? Everything that I say, I'm from here onwards, talk about energy and temperature, but bear in mind that all of this you can do for example, hard spheres, where temperature is not interesting, but playing the game with pressure and density. Okay? This is, I'm doing on purpose so that as the density goes up, you go down, just in order not to have to flip the picture, but that's all. Okay? In fact, in the papers, it is flipped. And more than that, often it's P and not 1 over P, but remember that what resembles a temperature is 1 over P. P plays the role of beta, or 1 over T. Okay, so what do we get? So these lines are there to symbolize that here, at these levels, you have many states. I'm not saying exactly how they're organized. I'm going to come back to this all the time, but please stop me if something is not clear. These are many, many states that appear. There is a liquid phase that, as you go up in temperature, goes up. At a certain temperature, the liquid phase encounters these many states, the energy of these many states. And here what you have is something, and this was the fantastic intuition that Kirkpatrick and Tirur-Malai had, that you have a state that is still the same but broken into pieces. Each one of those pieces is one of these states. I will come back, but do stop me, please, if you don't. Until when you go very much down in energy, you find states, but then you don't find any more. And these are the lowest. Now, if the temperature is sufficiently low, the lowest dominate your Gibbs measure. But if the temperature is higher, they don't. They are still there, but they don't dominate because temperature wants that the number of those states is important, and if you have many, you gain in entropy. So I'm going to go progressively with this same picture, show you the features. So this happens from now onwards in large dimensions and for the p-spin. So this is a cut of the picture I did before. Just I did these lines. Let me tell you what this means. It means that this upper level, which I am going to call threshold now, and it is a very important thing for what will come, you have shallow states that are roughly of a depth that has a lot to do with how much deeper you are than the threshold. If you are higher in energy than the threshold, you have essentially no minima, you have saddles. So you could have many directions that are like this, but some of them are unstable. So everything up here is unstable. As you go down, these states you find along this line, this happens at every temperature, get deeper, and you get to a point where you get the deepest of the deepest, and then nothing else. Okay? At the same time, if you compute the log of the number of these states you have, the density, when you are here, you find a very few that are the deepest of the deepest. This is a cut along this green line. And the log of the number goes up, so the number proliferates exponentially, so you have more and more and more and more, until at the threshold you have the maximal number. But then when you go higher still, you have more, but they are no longer stable. Okay? So the shallow ones are overwhelmingly the majority. The deep ones are many less, until when you get to a certain point, there's nothing else. So they get deeper and deeper, and they get rarer and rarer. This is, by the way, the structure of all interesting optimization problems, sort of like, you know, SAT, or for those of you who do that, you have less and less that are better and better from your optimization point of view. From another point of view, let me cut slices like this, along the green line, but now I'm looking at the landscape and I cut a slice. So imagine I cut a slice here, just above the threshold. Imagine that I have a landscape like this. And I said that above the threshold level, I had no minima. So if I cut here, you see that I see a connected region, meaning that the dynamics, while it's still at that energy, out of equilibrium, but it's still at that energy, is free to move wherever it wants. And as I go down, when I touch the level of saddles, you can see that it's precisely the point. Above there are saddles, here you find the first minima, and the vast majority of them. It's precisely the point where this system disconnects. Because you see that when you cut a saddle, your system precisely disconnects just below.
What is the horizontal axis?
It's all the configurations you have. And the vertical axis is free energy, but if we are at sufficiently low temperature, it's even energy. So these are the configuration, the positions of the particles, and if you are in large T, and this is, let's say, the energy, okay? If it's at finite temperature, you have to adjust a little correction because of entropic reasons, but it's not important. So energy is okay. So you see, this disconnection of the, and this is a big, big, big surprise. This happens without you putting it into the model. This happens in the p-spin, and it happens in large dimensions for spheres. You get this structure of threshold, many, many states, less, ground state, and then nothing. All these are stable. Actually, they are up to corrections that will come out in 5 transparencies time. So they are uncritical for the moment, except the ones at the threshold, which they are critical because they are precisely undecided whether to be a saddle or to be a minimum. You know, just above you have only saddles, just below you have minima, so these are very flat. Okay? Please stop me because this is quite important. This is, as you see, very technical. It comes out of calculation, but it is important to see the geometry of the thing. So here is the only place for the moment where these models are critical. All these states are, if you happen to be in one of them, they're round. If I look at them as slices, these up here, everything is connected. Down here, it is barely disconnected because you're just in the very shallow ones. And when you get down, they are very, very disconnected. Yes?
So the energy of the threshold is a local thing, or happens that it's the same for all the...
It happens that it is overwhelmingly dominating so that you can say that it's the same for everything, and this is a discovery that was surprising. Yes, indeed. And it is at the basis, I will talk more than enough about this, but it is at the basis of the fact that dynamics is what it is. Okay, so now we have a mixture. You have the equilibrium line, which is what it is, and you have this structure at every temperature. Now, I will convince you in a second that at intermediate temperatures, a cluster of states dominates, but you still have a liquid phase. So as I go down, now I'm not going down like this, like in an experiment when I'm doing a quench at given temperature, but I'm going slowly down in temperature. So this is all connected, but when I arrive here, I'm touching the threshold, so my phase space disconnects. But if it disconnects, I cannot visit everything by definition of being disconnected. So what happens? I cannot equilibrate. But still, I am going to convince you in a second, that I will try at least, that this is still liquid. So everything I have from here downwards is a non-ergodic liquid until the equilibrium takes me to the lowest state. And now when the lowest states, at the temperature at which these lowest states are dominating, then these are the very lowest. And here, nothing more moves. I will be around the bottom of the bottom, and this is the thermodynamic glass phase. So here you see the two temperatures of the p-spin and of this. that I had advertised before. The dynamic temperature is a first place where the phase space first breaks, and the static is the place where the states that dominate for the first time are the lowest of the lowest. And I cannot go down because there are no more states, so now the only thing that happens when I go down in temperature is that I am frozen. Okay? But what happens with dynamics? Now, dynamics, I go slowly, and I manage to equilibrate. When I get to this point, you see here, I am beginning to face a phase space that is beginning to be disconnected, and will be more and more so as I approach this point. There's going to be a slowing down. I can equilibrate up to the very last point, but here the dynamics is going to be slow because I am in a phase space that just barely allows me to move. This slowing down is the slowing down of the dynamic of what is called the mode coupling transition or the dynamical transition. We will find that in d dimensions, in high dimensions, mode coupling is not quite exact, but in the neighborhood of the transition, essentially the phenomenology is right. What is not right is where is the transition, but that's something that I'll come back to. So here there is slowing down, and down here it's much worse. If you start in a state like that, an equilibrium state, so what I just said is that the liquid, as you approach this temperature, here in equilibrium, you get what is called the mode coupling transition, and here there is the dynamic freezes. Now, what happens if I do this at finite speed? Well, at finite speed, you see what happens. I am here. Well, let me make it easier. Let me just be more brutal and quench the system at a given temperature. So what I am going to see as I go down is this succession. I'm going to start in a connected region, and then will find myself just the moment at which it disconnects. But by construction, if I could arrive here, I wouldn't move anymore. So what is it that happens in reality, and why do I have aging? What happens in reality is that something much more subtle and that wasn't guessed before dynamics was done, that you get slower and slower and slower and slower and never get below that level. Why? Because your system, your phase space is getting less and less and less connected, and because it's getting less connected, you move slower. But because you move slower, you don't go down, and because you don't go down, it disconnects, but more slowly. So this approach without ever arriving to the threshold is what the aging dynamics does at the mean field level. It is a bit subtle. So if you do an annealing, the same thing happens. At the beginning, you can follow in equilibrium, and then here, you age. Age, what is to age? Is to find yourself in ever different situations, but each progressively new situation becomes much more difficult than the previous one, so you spend more time in it. Okay? So this is liquid dynamics, as I said. And now imagine you are in this intermediate phase where the liquid dominates. Some of these states dominate. I'm going to tell you why. If you start in one of these states, you stay there. So it is a liquid because the thermodynamic values are liquid, but if you started in one of those, your physics would be very, very different. You would be in a deep state, and you won't be able to move to the other deep states. The Gibbs measure, the Boltzmann-Gibbs measure, which simply does a flat averaging, doesn't tell you how you get to the places. So it counts everything, and in counting everything, gets the equilibrium value. But there are doors, there are walls closing your phase space. So a calculation is a calculation of a thing that is fractured, a phase space that is fractured, which has the same volume as it would have if it would be a pure liquid. So when you do the calculation, this gives you the same things. But actually, if you're doing dynamics, when you start in one of these regions, you don't move at all. Yes?
So I understand that you're saying that in this non-ergodic state, you're stuck in like a fraction of your phase space. But why would the dynamics necessarily be slower? It would seem like the
No, it's not slow. You're right. Within your states, it is not slow. It is infinitely slow in getting to another one.
Okay.
That's very important. The dynamics in one of those states is as boring as you could possibly have. It's not critical. It's fast within this scenario. I'm going to come back to this also, but it's very boring. What is not boring is the fact that you are not able to explore the others, which you should if you wanted to reproduce the equilibrium results.
Okay, thank you.
And what is aging doing?
So when you are inside one of these, you don't age anymore at this level of approximation because you stay there. Unfortunately, you didn't explore everything, but in fact, if you started from the liquid phase, you don't get to that place. You get to the place where, that's why the name threshold. There is a percolation threshold of your states, of your phase space. So as you move to slices that are progressively more disconnected, if we were in the 80s, we would have called this self-organized criticality. We don't do that because it's out of fashion now, but it is a kind of that. You are approaching a critical situation, and the more you're close to it, the more slowly you move, so you never go beyond. Yeah?
When you move more slowly, when you're aging,
Why do I?
then if the dynamics in each region
Yes.
are the same speed,
Yes.
then the transitions are getting better. Like,
Exactly. Exactly. So you are moving in situations where if you want the transitions, you have to picture this in high dimensions. So it's not that your space does this, but there are fewer and fewer. Your bridges have lower and lower dimensionality, yes. But so the dynamics gets boring inside a state, but the passage from one to another gets harder and harder. None of this is phenomenology. This is all, you can do calculations, which is going to be the second part of my talk. But I'm not going to do calculations, I'm going to tell you how we know. Yes, sorry.
So, in this threshold, is it okay to say that KT of the order of the value?
Yes. Yes, it is okay. Yes. Yes. You just barely have the to pass. So why did I say, I repeated many times, that here you're in a liquid phase? The reason is simply that you count. This is again the picture of the number. This is the free energy of the states inside each one, and this is the log of the number. And you know, you have to maximize, you have to minimize the free energy, but maximize the number, no? It's like when you do any thermodynamic calculation. So the log of the number. So this maximum is achieved in an intermediate place here, so many states together contribute to your measure, but they are disconnected, and this we know from dynamical considerations. So a disconnected set of things is dominating your measure, but you as a walker inside one of those never get away. In the liquid phase, everything is okay, the doors are open, and then as you go down in temperature, there comes a moment where exactly this happens, that entropy, of course, is multiplied by temperature, so it counts less and less, and you get to a point where the best you can do is to stick to the bottom of the bottom, and this is the static transition. This is why I say that this is a liquid phase for thermodynamic reasons, not for dynamical reasons. For dynamical reasons, it is non-ergodic. So this transition here where you stick to the bottom, this is the Kauzmann scenario that I advertised before, that Kauzmann had sort of fantasized and never took very seriously, apparently. And it is materialized here by this thing. So the two things, the disconnection with temperature and the end of this curve with this intermediate phase was what was recognized by these people, and it's a remarkable fact. Two ideas that were disconnected, and even the communities that did them were disconnected, are in the same model. So below this temperature, equilibrium is dominated by the lower states. Of course, what I said about the lower states is the same as you can say about any of these. If you are in one of those, you don't visit the rest because they are isolated. So this, but the point that I want to make is that if you did a calculation, or so we used to believe until 3 transparencies more, this is not critical. So for reasons that are interesting that I will tell you later. Furthermore, and this is important for the next few days, you still have this limit. Remember that here I put temperature, and of course, as I go down, I can go to 0 temperature, and I have those states. Or I could go up in pressure. Remember, this is 1 over P. So I could have infinite pressure. If I had hard spheres, this is possible. And these are different states that I find along this line. Why am I insisting on this? Because there are, in this Simon's collaboration, specialists of this line. This line, which is the infinite pressure and surroundings and or 0 temperature, has the advantage with respect to other lines here that it exists. So this already makes, as you will see, a difference. But because there is no problem in having many states at 0 temperature. Now, once the liquid dominates, what are these guys? For example, if I am here, everything is forgotten. You have a nice, beautiful liquid, but you still have these states. Are they, in any sense, real? Well, turns out that these states are the mean field version of something that was very much emphasized by David Chandler and Juan P. Garrahan, that even when you are in a liquid, you have spots that become almost solid, like immobile regions. Well, I'm just mentioning that these states are metastable solids, so they are pieces that crop up, or patches in your system that are more solid than the rest, and then they die, and then they are born somewhere else. They are represented by this. And the highest one of those gives you a temperature that is studied by them. So I'm not going to come back to this, just a side mention. Okay, so now real life. This is why I told you about 0 temperature things existing, is that, as I told you, you should have said, yes, but this cannot be true, because I cannot have a state that has free energy that is higher from another one. So something is wrong in what I am saying, indeed, and the reason is that it was a large depathology, the fact that I fall in the threshold. What happens in real life is that you go a bit deeper, and deeper, and deeper, and deeper, but then it gets more and more, the time's longer and longer, and at some time you stop the experiment. But this penetration inside these states, so whenever I said before, I am locked in a state that cannot move, you should read, cannot move in d dimensions, but once I go to dimension 12, Patrick can swear that you, in practice, cannot move. But truly, you will eventually escape, because, as I said, you cannot really have states that are metastable order 1 free energy. So it's a mathematical necessity that real life, you do penetrate under the threshold. And it is like a kind of moving threshold that is going down, because these doors are not literally closed at finite d. What happens is that these barriers are exponential in d, so in the dimension, so it takes longer and longer. Okay, so this is why I was saying that the whole thing is subtle, because you have a construction which is already subtle, but then on top of it you have to argue that it is not quite true and it's a bit metaphoric. Okay, so this is what makes something, okay. If you are here, you will eventually get to the liquid, and you discover that the liquid here is not, after all, completely non-ergodic. It is ergodic, because you cannot have an exponential number of metastable states, argument number 2. So the region is connected, but you can think of it as being connected through processes that are very, very, very slow. So if you want, the whole scenario is a liquid where everything moves fast, a transition that is no longer there because now you can cross these things. So the dynamic transition cannot really exist. It is a kind of place where it seems that you're slowing down, but not quite. Then as you go down, you have processes that take much, much longer, and only when you, if and when you get to this transition, which you never do, you would feel perhaps a true transition. But we don't even know that. But anyway, the orange lines is one of the things that we should learn how to calculate, and we still do not know how to. We do not know how to do the dynamics getting inside. We know that it has to be so, but we still technically do not know. We can do it numerically and estimate things, but not analytically. But this will be done. I don't think it's impossible. Maybe it will be done in the next few years. So, all in all, what remains of all this scenario if you really want to pull it down to finite dimensions? Liquid, very viscous liquid, very viscous because you still can find your way between states, but only through things that are very, very suppressed in the large dimension limit. Until you get to this point, maybe there is a transition here, we don't know. This transition here, the mode coupling one, disappeared because you don't have anything really special happening. Mostly I would say that the mode coupling data are in the eye of the beholder when you look at simulations. And then you go down here, maybe there is an ideal glass transition with states. Here it is possible because you are looking at the very lowest that are not really metastable. Maybe, but we will never do an experiment that arrives up to there. This is complete, this is the problem, that we don't have any system which we could really thermalize up to here. In a real experiment, I would go down, and then at a certain point, I would stay hung up here, because simply I don't have the time to go through. But as I go to infinite temperature, these states, which I told you couldn't exist, but they cannot exist at 0 temperature or at finite pressure, but they are perfectly well allowed to exist at 0 temperature. The nucleation argument, you will see that doesn't need, at 0 temperature, there is no bound, because you need a bit of temperature to be able to jump the barrier. So these guys exist, no doubt, even in finite dimensions. So it's a very particular line, but as I told you, it has the merit of existing. Okay? Yes, yes, yes. So, question was, why do I call this an ideal glass, assuming that this exists? Because this goes back to the original question. If you arrived here and there was really a transition here, then what you would have is a thermodynamic transition between this line and this line, and a transition to what? A transition to a glass, which would be ideal in the sense that it wouldn't be something that will die eventually with time. It would be a true, if this existed as a separate phase, as a true different thermodynamic phase, which you would consider as a solid, and there really the barriers would be separated well. And if such a thing exists, but if such a thing exists, as I said in my very first slide, you would really need a correlation length that diverges. Otherwise, this cannot happen. But why don't I know? Because as I go down here, I fall out of equilibrium, so it's as if I derail. And of course, given time, I will fall, but this is hopeless. Okay.
So when you reach that bond state, the ideal glass, what am I supposed to be thinking about the ideal glass? Is that a configuration of particles? Is this
it's the optimal.
What kind of thing are you?
It would be disorder, but it would be the optimum, barring crystals. So for example, make the particles polydisperse. Imagine there is no crystal. This would be the optimum of all, the best of the best, and essentially it would remain unchanged up to 0 temperature. Now we don't know if such a thing exists as a separate object to the rest, where you really have a true solid that lives forever. You prepare it and it's like a crystal, it lives forever.
But is it one configuration of all these particles?
It's a very few. it's a very few. So what you get from the replica calculation here is that there is one configuration that takes half of the probability, another one that takes a quarter, another one that takes a tenth, but essentially it's broken between a few.
So that zero temperature, the world
Yes.
states, could it be possible one of the states represented as a crystal phase?
Oh, no, sorry. Crystal phase, I didn't put it, would be somewhere below here, we believe. We don't know. And it would move here. What is true is that in high dimensions, like 4, even 4, you don't see the crystal. It is so separate, so far away, that you never crystallize, even for hard spheres. But you have to argue that crystal is out of the game. If I can make it to the technicalities, I will tell you how you kill the crystal. But okay, so there is a problem, though, that I said that most of these states, once you were inside, are boring and uncritical. But now there is a problem because we know that, first of all, when you look at the data of liquids and gases, of frequencies that are very low with respect to the microscopic motion, but very fast with respect to rearrangements, you have a whole lot of phenomena of semi-slow relaxation that exists. And I told you that once you were in one of these states, there was nothing interesting going on. So we have a big problem, because even if you were in real life in a place like that, we know that very big, many scales of slow relaxation in the susceptibility data, for example, exist. So the question is, why aren't things there? Is it that large dimension, this phenomenon you cannot see, or is it that something was missing? Secondly, the J points, the green line, when you do it for hard sphere, the people who are specialized in the green line had observed and argued and convinced everybody that those points were critical in a way. Why? Because if you do a packing of things that are solid, you will probably hear about this, they are just marginally stable, there is isostaticity. I'm not an expert on this, but the point is that these things were critical in the sense that if you move a particle, you get enormous rearrangements. But as I told you, we thought there was no criticality within the states. So this was either a mean field pathology, this is the eternal question, or something was missing even within mean field. So enter the Gardner transition. Elizabeth Gardner was a young woman who discovered this, and then she died very, very young in '89. So she discovered it actually in a p-spin, but we now know that it exists in large dimensions. So the Gardner transition is exactly each state, as you go down in temperature, there comes a time where it becomes flat. This is not in the scenario I did up to now, and then it breaks into pieces. Just exactly in the same way that the paramagnet becomes a spin glass. So what I did at the very beginning, what I told you at the very beginning, that the spin glass transition was this way, somewhere below here, you begin to have states. Each of one has its own kind of transition of this kind. And so, even within mean field, this is something that we know since not so long ago. So how would you interpret this? If you have to picture it in your mind, you would have to think that I have a disordered matrix of points, a disordered. And at a sufficiently low temperature, all of a sudden, I have small excitations, these are in gray, and they are coupled with one another in a way that kind of makes a kind of spin, network of coupled little motions, and this creates a kind of spin glass without even changing a spin glass, but not of spins, but of small excitations. This would be the way to put it in real space. And these excitations are all coupled to all, at least in large dimensions, and you would get a kind of many states, meaning that within the same basic structure, you could rearrange these particles by very little in many possible ways. This happens in the solution, and so this adds a new element. I'm sorry, but so that if I follow the states, they are, as I told you, uncritical, etc., but you get to a whole possibilities of values where the states break, each one of those breaks into many, many substates. So essentially you have big states separated by, as they were before, but they, inside themselves, become critical. It's a very surprising thing. And again, it shows you once again how this way of doing things, you not only argue for things, but the system itself kicks you back and surprises you with things you didn't expect. This happens without you imagining it. It happens in a calculation. This is, I would say, the power of the whole approach, that many of the things happen even if you don't want them. But in this case, they are very welcome, because these states, the ones at infinite pressure, we know that they are critical. We know that they are marginal. We know that a very compressed system of hard particles, if we move one particle, it creates rearrangement. This was done a lot here in Chicago, and Mathieu is going to talk about this? No. Mathieu is going to... Yeah, okay. So you will have a lot of that. But it was a complete disaster before, because it would seem that none of this, except at the threshold where the states are marginal, but all these that are low didn't give anything marginal, and that was a real shame. It could have been because in large dimensions it doesn't work. But once you introduce this transition, you don't introduce it, just note that it happens. Now all the states you find in this orange region, on top of it, are no longer uncritical, but they become critical. So even the boring dynamics to which I referred before, that you have on one state, becomes unboring. Okay, this is part of life. And if you were sitting in one of these states, you could possibly, within the glass phase, you could possibly have, and we don't know this, but we could possibly have all these kind of dielectric intermediate frequency things happening. So all this life in the random first order scenario, as it was till some time ago, there was no life within a state. You had an exponential relaxation and you were dead, and there was absolutely nothing interesting happening inside. Once you realize that this transition happens, then you have lots inside these states, because they now have excitations that couple and produce a transition. They break, they have a lot of possibilities of slow relaxations inside. All this is partially done, partially work in progress. So just to give you an example, one possibility for the intermediate frequencies that could be a model where you could see things. This is not us, this is many people have conjectured that if your particles were a little bit distorted, then you would have a matrix of positions of particles, but then you could have the rotations. And these rotations couple in bizarre ways, because of course what is more comfortable to a set of particles that is already disordered is complicated. So you could have a kind of, and now I'm doing a metaphor, a kind of spin glass where you would have the positions, and the interaction between these spins would be the position of these particles, would be random. So it would be like a spin glass sitting on a glass. That was basically the idea that people like, probably, I don't know, Goethe and then Cummins and had about what could be part of this Garner transition. When would it be more observable? When you would have excitations that have to do with turning the particles that basically don't move them but interact with one another, because when you turn one, it disturbs another, and this could produce. So this model with spins is being studied by, which is a metaphor of this one, is being studied by Ludovic. It seems that it should give you a very strong Gardner-like phase. You have it even for spheres, but this one now would be very strong with lots of excitations. And another toy model that you can build of this one, which is the metaphor of the metaphor twice, is to make a p-spin just like originally the toy model was, and then on top of these make a spin glass, but where the interactions depend on the position. So this would be playing the role of the positions, and this would be some feedback which would create these spins, sigma, interacting through something that depends on the positions. So what I think is that this would, a bit more than think. What you can convince yourself is that the Gardner phase could even move, and that's the whole point of the exercise, into the liquid phase. So if this would be the case, you would have a liquid of states that you can jump between them because this is a liquid phase, but still each one of them has all this rich structure, which was absent in the original thing. You can convince yourself that in this model, I think you can convince yourself, we have convinced ourselves that in this model you really have a Gardner liquid. So this is an element that I bring here because, for one, Sid has done a lot of work years ago, on all this life that you have, even in the liquid phase, at intermediate timescales that are neither microscopic nor the slowest of the slowest. And all this was absent, especially in the liquid, but in the theory of random first order. A model like this shows you that it is possible to have a liquid, because this with activation is a liquid, that has Gardner structure, so it's a Gardner liquid. So this is why this transition makes us happy, because it seems that, of course, at any point you have the dilemma when you're doing large D that you don't know when there's something that doesn't work. Is it that I'm missing something in my calculation, or is it simply that in large D it doesn't exist? You don't know, because large D is an approximation, well, I mean, obviously, and you never know if the effect that you're looking for, it used to be believed that those effects of things happening in states, it used to be believed that it was simply not there, you had to work at finite dimension. It may be that, not really, that some of it you already see in the actual calculation, okay? Okay, so this is more working process, it's sort of, but so the morals of this is, to the original picture, which was complicated and subtle enough, when you have to take into account the picture plus the things in which the picture is only a metaphor because in finite dimensions it's modified, to that you have to adjust the fact that the Gardner phase brings in a whole lot of elements that move you close to reality but make the picture one step even more complex. Yeah.
I know it's a metaphor, but when you go to the sigma k, sigma l,
yeah.
Can you connect this value just -1 to the position of particles?
Exactly. So you want the metaphor of the metaphor or the metaphor? See. Okay. So no, I don't know how to do it. Maybe somebody does. What you are asking me is, can I map this into a spin problem?
Can you interpret the sigma k, sigma l?
Oh yeah, this is a metaphor of this, so these are interpreted as the spins that are there, and their matrix of interaction, which is random, but you put it on purpose so that it depends on the positions. Everything metaphorically speaking. Now, is it true that you can map, for example, particles that have some form of deformation into particles that do not have them, but with spins that interact? I don't know. The idea... This metaphor I don't quite know, and this metaphor is very metaphorical, so I don't even... Yeah?
So can I just make sure I've understood this regarding transition?
Yeah.
So you're coming down and you're lowering the temperature.
Even out of equilibrium.
And So you get stuck in some state.
Yes.
And what, if you had come down a second time, you might have gotten stuck at a different state.
Absolutely.
And you have all these different possible places you could be.
Yes.
And the statement is that inside each one of these things, at exactly the same temperature, this would break up.
Yes.
And that is in this dimension. So
Yes.
independent of which place you ended up, that barrier will
Independent, more or less independent to the extent that you go to the same region of energy, and yes, but independent of where you are, a typical state will start breaking into things. Now, if you want to picture this in finite dimensions, you would say, I have a matrix of positions that normally were okay, and now because the temperature is low, this breaks into, you know, buckling modes that talk to one another and behave a bit like a spin glass would be behaving.
But this happened once when you got into this place, you got to this state, right? But then it happens again.
Then there is the whole spin glass thing where the states keep on rearranging and it's a mess. But what you have is that forever and ever the system remains with many states, critical, and so with states that are changing, but without changing the big structure, they are changing and rearranging.
But each time it's critical. That is,
Each
time you lower the...
It's critical all the time now, from there onwards. It doesn't stop being critical. So all the way down or all the way up in pressure. What was a problem is that we didn't see how this could invade the liquid phase, and for hard spheres it doesn't. But we are fairly convinced that if you add other degrees of freedom, at least in the metaphor of the metaphor, which you can have this invading what is the part of activated liquid. We want it to be in a liquid because the things that we know of low frequency, of intermediate frequencies, are mostly in liquids. So it would be a real embarrassment.
Why the critical issue and just temperature and the time?
This one?
No, the temperature.
Here? This one?
No, the vertical one.
Ah, this one? Because higher than here, all the things that you have are maxima and not minima. Or if it's hard particles, there are situations where you are like this, but if you do like this, it would break. So
the jamming point is critical, only has one point.
The jamming transition gets critical at one point if you don't work hard. If you do a quench, if you don't work hard means if you don't really insist on doing a terribly slow quench. Ludovic has done this very carefully, going very, very slowly, and you get a J point that is a bit lower. It doesn't really matter because it has the same property. They all have the same property, so it doesn't change anything. But you don't get to the same, you get to the same level with the same protocol. But now multiply by 1,000 the times you take to crunch, or by 1,000,000, and you will get to slightly lower, and you will find some others, which will have exactly the same properties. Okay, so this ends my description. Now, do you want me to do a bit of what are the techniques by which we know this? I have some 10 transparencies. Can I do it, or say half an hour? Yeah? Okay, I'll be quick. So this is the more technical part. This is just making some sort of listing of things, because these things we know, all this picture, we've attacked, means a lot of people, have attacked this problem from very many angles. And even so, a lot of it we don't know how to do. I told you activated processes we don't know how to do. Okay, so there are two types of techniques. Dynamics, where you simply try to solve a system, in our case, large dimensions, starting from a certain configuration and letting it go in contact with a thermal bath and see what happens and try to solve it exactly. There is no mystery there. This is a calculation that repeats the experimental situation. It can be done. It's hard in some cases. What is amazing is that analytical results can be obtained, and the reason is that you have this kind of phenomenon. I think somebody asked this, and it's good to say it again. we now understand that this threshold line where things end, it is a geometric feature where wherever you start from, somebody asked me, is this everywhere more or less the same level? Yes. So you fall onto situations that are similar. It's not that each dynamical thing will take you somewhere completely mad and one time you're going to end up here and another one here and another here. If it would be that way, it would be the fact we understand now that dynamics is solvable at all is because this kind of levels that are very significant for dynamics exist and are self-reproducing. So, okay, that's for dynamics. Doesn't need to justify much. But now, there are equilibrium techniques. And this is a bit confusing for people who read the papers. Because, in principle, equilibrium, if you did a simple equilibrium calculation, what it can tell you is this line here and this line here. So if you do equilibrium like that, you are getting information, but information that is not awfully relevant because you are talking of a phase that you're not going to reach. So there has been in the literature, I would say, starting from Silvio's thesis probably, a whole panoply of methods whereby you adapt equilibrium, and in particular replica theory, mostly replica theory, to compute things that ultimately are out of equilibrium or dynamical. But what might be confusing, this is why I put confusing for non-specialists, is that the origin of those arguments is different. So I made a list, and I think it would help because it's never listed this way. So I'll make a list, and if somebody in the audience knows more than I, so we can add. So what does dynamics tell us to start with? At least in the absence of a Gardner phase, the importance of the threshold level, so that as the aging goes down, when the space begins to disconnect, you never go beyond, you just approach more and more this threshold. Second thing we know, partly from analytics, partly from numerics, is that, and this is crucial, I said something about Edwards ensemble, is that within mean field, the states that you visit at a given time, you visit them inside you are at temperature T, the temperature of the bath. But you are out of equilibrium, and you can say that you have visited them with a flat measure. This is by no means obvious. There is no proof for this. It's a fact that you can tell from solving the dynamics analytically in certain cases, numerically in another. So dynamics gives you this picture of mean field dynamics. You arrive towards a threshold where you visit the topmost states or the vicinity of the topmost states with a democratic way. And if you really insist on doing finite dimensions, you visit the lowest states painfully. You go down very slowly and painfully. But what is remarkable is that you visit them as if you were visiting them democratically at each time. So the system is as if it would be at a temperature, the bath temperature, inside each state, and cooling down adiabatically from the point of view interstate. So this is the global dynamics, the global image you have of dynamics. An adiabatic cooling of the visiting of states which themselves in their insides are visited with the bath temperature. This is, if you add the Gardner phase, then you have a bit of a mess. But at least you have that. So equilibrium, straight equilibrium calculation would give you this violet line. As I say, it's not very informative. So before telling you the strategy number one is that you don't want to do a calculation where the crystal dominates. You're not interested in the crystal. So one thing that happens often, and I mention it now, you will see it sometimes in the literature, is to add some form of disorder, for example, fields that are pointing in random directions, call them pinning fields. Do all your calculation with this disorder, and then send the disorder to 0. Within mean field, and only within mean field, you can analytically continue this to 0 field, And what is the advantage? That you kill the crystal, for example, but you can do more than that. Okay, so adding disorder and sending it to 0 is one technique that is used throughout and rarely mentioned, because we have all we're so much accustomed to this that we don't even need to say, because you don't really do the calculation with finite field and send it to 0, just you know how it's going to be, you set it to some form of 0 that implies what I have just said. What is unfortunate for maybe you is that when you read it in papers, you barely see a mention of this. This was mentioned, the idea, the first time I saw it is a paper by Kirkpatrick and Tirumalai, if I'm not wrong, a Physical Review Letters, the British, no? But then Monasson did it in its most clear and concrete way. Okay? So this you have to think of it. It's very analogous to how you treat metastable states in mean field. So it's very closely analogous to the methods of metastability. So once you know that dynamics is going to finish in the threshold, well, the threshold you can compute statically because you propose that you're going to calculate states, but you choose them so that they're marginal. Choosing them so that they're marginal, you bias the measure. It's a pseudo-equilibrium calculation in the sense that it's not giving you the equilibrium value, but you can inject your system into those states. Once you know, you have to know that dynamics does that. If you assume that it does, then a purely static calculation that searches for marginal states can find this line. Again, in the presence of a Gardner phase, this hasn't yet been done, but it will very soon, I guess. Okay, so that's strategy 1. Strategy 2 is this way of working with constraint measures. So, Silvio, you will appreciate my picture, I think. So what you do is you, for example, choose an equilibrium state, nail the configuration that you chose in equilibrium, and then look at configurations that you restrict to be at a certain overlap. This is why this pair of compasses to this one. So you see, this is a way of getting at barriers in dynamics. There are things that have to be said, but this way you can get some information on the topology, because clearly if the best you can do at a short distance is something very high, it seems very improbable that dynamics can go through. So this is a purely equilibrium computation. You first equilibrate a configuration, and then you compute another configuration, equilibrate, but with a constraint measure. If you do the log of the probability of this, you will get a curve that depends on Q. This is called usually Franz Parisi potential. This potential is telling you what are the typical heights you see at different distances from a reference configuration. It's an equilibrium calculation that is tending, it's going towards dynamical. Another different thing, that this is more Monasson's idea, you equilibrate the system at a given temperature in the presence of a given pinning field, and then you put those configurations at a different temperature. So you use this as a potential, which is the input from another temperature. So this is morally the way to do in equilibrium this. So if you assume that this happens, this only dynamics can tell you, because for the moment there is no theorem that says that this can be done this way. But if you assume that it can be done, that that's the truth, then you can shortcut everything and do a purely equilibrium calculation that does precisely that. It chooses the height, so the inside measure measures each state, and then this TF is the outside temperature. So all in all, it allows you to measure this. But as I say, it's a mixture of an assumption based on what dynamics does, which for the moment we don't know how to prove in general. We know how to solve a problem and say that actually it is doing like that. And then when you change model, you say, I guess it's going to do the same, and then you do this calculation, okay, with an equilibrium calculation. Then there is yet another one, which is completely different in origin, or at least as far as I can see, completely different in origin. It's the following, and this one is purely technical. You have certain diagrams, certain integrals that you have to calculate that you can represent with diagrams, and that, for example, in mode coupling give you the exponents of different decays. You have to calculate, your job is to calculate those. Somebody does the job, and he found long ago that in terms of the coefficients of these different diagrams, the critical exponent is such and such. Okay? So this is a purely dynamic thing. Now you recognize that the diagrams, the topology of the diagrams and the coefficients that enter dynamically is the same as the topology and the coefficients of diagrams that enter if you did a calculation with replicas. For those of you who don't know what replicas are, it's a static calculation. That's what all we need to know here. So once that you know that in terms of these coefficients, such and such a dynamical exponent is given by such and such a formula, you can very quickly, or much more quickly, calculate directly these coefficients, and then you will use the dynamical formula directly from using this as a generating function. This is yet another technique. I'm not giving you the names of everybody who did what, but if necessary, I can. You did? No? Okay. So this is yet another one, and I put it here because A, it's useful, and B, it's in essence a bit different from the other. And then last one I will do is an observation. In fact, this is a paper of Silvio, Giorgio Parisi, Silvio Franz, Luca Peliti, and I think nobody else. Marc Mézard. It's not exactly the way it's put in the paper, but I think that you can translate it, or at least the essence is the following. Because of the nucleation argument, the free energy in times that may be incredibly long but don't diverge in the thermodynamic limit have to go to the equilibrium value. So it can differ from the equilibrium value only by a small quantity of order 1. So if I am cooling a thin glass and I have 10 years and I see the curve of decay of energy, for example, and I extrapolate it, the value to which energy density, the value to which it extrapolates is the correct equilibrium value. Now I can do the same thing but with a little field or with another little field. The conclusion you get is that all susceptibilities, static susceptibilities, if you extrapolate them to long time, per particle, go to their equilibrium values. Of course, in practice, you're stuck somewhere there. You don't you cannot really extrapolate much in real. But the fact is that, in principle, the equilibrium values of susceptibilities in equilibrium are the ones that a finite dimensional system reaches in long but order 1 times. There are exceptions, and those exceptions typically have to do with symmetry breakings. For example, if you do it with a ferromagnet, it doesn't work, but that's something you understand why. So this is another argument that actually has consequences, which I'm not going to, but it's different in nature from the previous ones. Okay, so to finish, so I gave you this panoply of methods whereby one uses statics to infer dynamic information, because I don't know of any place where there is a list like the one I've done, and I don't know if I'm missing things still. But it gives you an idea of why you're doing this, because often people ask you, but you're calculating things that an experiment doesn't reach. Well, this is how this is how an equilibrium calculation attempts to get at dynamical things. Okay, so what are we missing? I was asked to say what are we missing. To my mind, there are two things. One, in gray, the things that we don't know how to calculate today. Some of them are easy and I think will be done, like for example, what do you do with a Gardner transition in some cases? This will be done. Some are harder, like activated processes. This is maybe won't be done in the next 10 years or so, but you know, one day somebody will do it. But then there are other things that, to my mind, are a bit, with respect to this scenario in particular, are a bit more fundamental, which is the things that are matter of principle. So let me list some things that are matter of principle. When you talk of states, now we know that these states are not stable. So by principle, they cannot be stable. And we are counting the log of the number of states in order to find the complexity and then find a transition. And I've used this before. But these states and the log of their number exist only in infinite dimensions. So what log of what am I going to calculate if I had to invoke them in finite dimensions? I don't know. This is true of complexity, as I say. You have to calculate the log of a number of states, but as I told you, the log of the number of states per unit, per particle cannot be finite because you cannot have an exponential number of stable states. So you would have to say, well, I'm going to calculate the log of state, the number of states that live for at least an hour. And that you can do, but that's a bit ugly, to say the least. So barriers, as I told you, the nucleation argument tells you that barriers are order 1. So all this thing where you had all the minima and all the saddles cannot possibly be literally true, because just the nucleation argument tells you that the worst you can do with a droplet is finite. Pinning fields that are used often in connection with justifying some static calculation, actually you cannot do this analytic continuation in finite dimensions. This is the problem why a Langer calculation is not used in finite dimensions for ferromagnets, because what can you do? There is no continuation that way. There is a level at which the pinning field is so weak that in finite dimensions, the droplet is more favorable. So you should decide how strong you make the pinning fields depending on what time scale you want to see, but this is going to be very dirty. Similarly dirty as with respect to the previous things. And we know that mode coupling transition is gone because we know that you cannot have this transition at states that have high free energy. So we know that mode coupling is just, the dynamic transition is just a ghost that exists in large dimensions. What can we say about Gaussman transition, the one below? We don't know. It could be that for equally fundamental reasons which we do not know today, it also is gone. The prejudices are varied depending on with whom you talk. Of course, an experimentalist can say, what do I care if I'm never going to go to that transition, and it would be relatively justified. So what I want to say about this is that this whole scenario we describe, actually some of the entities are mean field in their very definition, not only because we are incapable of calculating better than large dimension, but also because their nature, they exist in a clearly defined way only in this limit. So this is something to bear in mind, and I don't know what is the answer, but at least it is clear that there is a difference between open questions because of calculational reasons and open questions because of matters of principle. So with this, I let you in peace.